Okay, section 1.3, you're going to need this Exploration 1.3 worksheet, Introduction to Definite Integrals. This can get put into your notebook under a folder after, or whatever you'd like to do with that. Okay, starting the situation, and we're going to be moving away from derivative today, and we're going to talk about definite integrals. Remember the three things I told you are in calculus? Limits, derivatives, and integrals? Well, now we're going to hit integrals. So it says, as you drive on the highway, you accelerate to 100 feet per second to pass a truck. After you've passed, you slow down to a more moderate 60 feet per second. The diagram shows the graph of your velocity as a function of the number of seconds since you started slowing. So we've got velocity on the y-axis, and that was given in feet per second. And the time was given in seconds since I started slowing down. So past the truck, now I'm going to hit the brakes a little bit to slow back down, and then hit my cruising speed here. All right, first question. What does your velocity seem to be between time equals 30 and 50? 30. My velocity, remember this is velocity, all I got to do is read the point, is 60. And all the way through here, I'm at my cruising speed of 60. So right here, I'm at a constant 60 feet per second. How far do you travel in the time interval from 30 to 50? Well, we're looking at a distance rate time problem, Algebra 1. If you remember, to get distance, that's just equal to your rate you're traveling at times the amount of time that you're traveling. Well, we just figured our rate was 60, and the amount of time from 30 to 50, that's 20 seconds. So that would give us 120 feet would be the answer here, because I'm multiplying. And I can show you how the units cancel. Because this was 60, I'll put them right here, feet per second, multiplying by seconds. I'll make that over 1 since it's next to a fraction, and you can see the seconds cancel out and leaves you at just feet. So we traveled 120 feet in those 20 seconds. Okay, it says, explain why the answer to problem 1 can be represented as the area of the rectangular region of the graph. So what they're talking about is from 30 to 50, we want to box this in. And when you box it in, you get a nice little rectangle. And if you look, the area of a rectangle is length times width. Well, my length across here, if you want to call length, I guess that's width, is the 20 seconds. The length or the height, that's 60 feet per second. And so I'm just multiplying to find the area of the rectangle. It's a 20 by 60 rectangle, and you multiply, you get 120. So the whole point of this is a way to, well here, before I talk too much, it says the distance you traveled between 0 and 20. So we're looking at the beginning part of this graph from 0 to 20. Can also be represented as the area of the region bounded by the curve. So it's the area under this curve here. The problem is this is not a nice shape for us. It's a nice curve chopping these blocks up. So what we're going to do is count the number of squares in this region. We're going to estimate the area of parts of squares to the nearest 0.1. So for instance, how would you count this square? So what part of this square is shaded to the nearest tenth? So if I was to estimate this, it definitely looks like it's over half. I would guess it to be about 0.6. 6/10 of that is shaded. So what I want you to do now is hit the pause button, and I want you to count all of these squares here. What I would do is I would count all the full squares, then I would fill in the partials with what I thought they were, estimated to the nearest tenth, and then add them up. So go ahead and hit pause, take the time to practice this skill. I'm going to do it quickly without showing you, so I'm going to pull this away and do this super quick, but you can hit pause and then turn it back on when you're ready. Okay, I got a total of 25 full squares, and when I added up all my partials, I got 3.8 for a total of 28.8 squares. And if you need to take a look at mine, you can see what I estimated some of mine at. The actual answer is 28.6. So my estimating isn't perfect, but again, we're just looking for being in the ballpark here. So 28.6 is what the author actually had when he did the partial squares. Okay, so our goal was to figure out how far we traveled from 0 to 20. All I've got right now is the number of squares under the curve. That is not my distance traveled yet. This is going to lead us into it. It says, how many feet does each small square on the graph represent? Well, if you think about it, each square, take a look at the size of one square. They're counting by 5s down here, so that's a distance of 5, and they're counting by 10s on the vertical. So when I multiply, I get 50. So each square, 10, is representing 50 feet traveled. So I know how many squares there are, 28.8. Each square is worth 50 feet. So all I've got to do is 28.8, or take your number, whatever you got, multiply by the area of a square, and what do I get? 28.8 times the 50, 1,440 feet traveled. Because remember, what I'm doing is multiplying feet per second by seconds. They cancel, I'm left with feet. Okay, so there's your process for doing definite integral. You're going to take the number of squares under the curve, number of squares, and then multiply by the area of one square. So when you do an integral, what you're actually doing is multiplying the y variable times the x variable. When we did derivative, we were dividing, change in y over change in x. Okay, on to the next one. Problems 3 and 4 involve finding the product of the x value and the y value for a function where y may vary with x. When they talk about that, because y is not a constant here, it's decreasing, 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 slowing off, where here y was a constant value all the way through. It was easy to find that area and that distance. Here it's changing all the way through. So we have to do that counting business. Okay, such a product is called the definite integral. So the author's just giving you the definition here. When you multiply x and y together, you're doing a definite integral. Based on the units of t and vt, explain why the definite integral of velocity with respect to time has feet for its units. And that's what I tried to show you all the way through. So the velocity is in feet per second, and we are multiplying by seconds. And I can put a 1 under it and not change it. That way I can see that these seconds are going to cancel each other out, and I'm left with feet times 1, which is just feet. Okay, let's practice one more. Number 6 says the graph shows the cross-sectional area, y square inches, so y has square inches, of a football as a function of the distance in inches from one of its ends. Okay, estimate the definite integral of y with respect to x. So, all right, so definite integral is area under the curve. So I need to count squares and then multiply by the area of a square. Okay, let's be clever with this one. I would, because I see it's symmetrical, I'm going to count half of it and then double my answer. Okay, again, I want you to hit pause on the video. I want you to take the time to go through and count this up and then compare it with mine. So go ahead and hit pause. I'm going to pull this paper away. Okay, when I counted, I got 44.8 squares. The author actually said it was 45.2 squares. I am looking for you to just be in the ballpark, okay? Just not way far away from these answers. All right, after that, we have not found the definite integral yet. All we did was count squares. To find the integral, I've got to multiply by the area of one square. So if I look at the size of one square, doesn't matter which square on this graph, the size of a square here is they're counting by ones here and they're counting by fives here. So the area of one square is 5. So I'll go 44.8. You take your number. The area of one square is 5. I'm going to get 44.8 times 5, 224. If you had 45.2 times 5, 226. Okay, so now we want units on this answer. So when we do integral, we are multiplying the y variable times the x variable. Oh, I put x. Inches. Okay, so I've got inches squared multiplied by inches again. So inches squared multiplied by inches, there's no fractions here, nothing cancels, I get inches cubed. So it's giving me the volume. How much volume a football has as I move through from the end of it to the other end of it. Okay, what are the units of the definite? Oh, I already did that, just did that. Inches cubed. And he's hoping that you remember that to be volume. So, what did you learn as a result of doing this exploration that you did not know before? Well, here's the big idea. The definite integral can be found by taking the area under the curve. Your process is to count squares and then multiply by the area of one square. Okay, we are not done yet. Okay, save this backside for when we get to section 1.4. That's another day. We'll take that out. But continuing on in this section, you are going to need a little bit of graph paper. Example 2 is number 10 in the book. Well, I think I gave it as a homework problem too. I'll have to take that off. Hold on while I get it. Okay, this is our number 10. We've got two kids on a slide here. It says Phoebe sits atop the swimming pool slide at time 0 and she pushes off. Kelvin ascertains that her velocity is given by 10 sine 0.3 t. I don't think he's that smart, but anyway. Where velocity is in feet per second, Phoebe splashes into the water at time 4 seconds. Plot the graph of function v. Don't forget to set your calculator in radian mode. What are the domain and range of this velocity function? How fast was she going when she hit the water? Approximately how long is the slide? At approximately what rate was her velocity changing? What special name is given to the rate of change of velocity? Okay, there's a lot of stuff going on in this problem. So, let's start by, okay, I'll pull this away. our equation is, get this all on here, the velocity with respect to time is 10 sine 0.3 t. Okay, we'll let the calculator make a table of points for us that we can graph. So we'll go y equals, typing it in, 10 sine 0.3x. I better check my mode. Check your mode. I'm in degree. I need to be in radian mode. We're in radian mode for all of calculus. We never switch out of it. Table set. I know this is going to start at time 0, and it's going out to 4 seconds. I'm going to go by every half second. You get to set that. Okay, so table. Okay, so I'll copy this down. So I got time and velocity, 0, a half, 1, 1.5, 2, 2.5, 3, 3.5, and 4. And she hits the water, and then the equation means nothing to this problem anymore. Okay, distances. And we're just doing a graph, so I'm just going to go 1.5, 2.96, 4.3, 5.6, 6.8, 7.8, 8.7, 9.3. Okay. Now, because we're going to be counting squares here, we want to make a nice accurate graph. So my velocity, I want to go up to 10, and my time is going out to 4. So I'm going to make a nice big graph. Again, you get to make the graph any way you want. The more accurate, the better your answer is going to be. So because it's going up to 10, I think I'll count by ones there. And then on the x's, because I'm only going out, I think I'll probably count by halves. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4. Okay, just plotting the points. 0, 0. Oh yeah, you should have went and grabbed some graph paper. Pause the video. Oh, well, too late now. I'm sure you did that. A half. 1.5. 1. Almost 3. 1.5. 4. 3. 2 is 5.6. 2.5 is 6.8. 3 is 7.8. 3.5 is 8.7. And 4 is 9.3. Okay, looks like this. Okay, she hits the water, so our graph ends. Okay, so there was part A, plot the points. Plot. B, what are the domain and range? Domain, remember, is your x values. Our domain, we started at time 0 and went out to 4. Range, low to high on the y's, 0, and our y value 9.3. Now let's see, label this. Let's see. We had feet per second here, her velocity, and we had seconds here. Part C asks for how fast was she going when she hit the water? How fast at water? Okay, how fast is the velocity? Now before, when I was kind of training you how fast derivative, but they're giving me velocity over here. So all I need to know is that she hits the water right here at time 4. So she was traveling at 9.3 feet per second. Approximately how long is the slide? Here's the tricky question. This is a distance question. How far did she travel? Because her distance down the slide is the traveling. This is not the slide here. Well, if you think about it, if I've got velocity and time, we just found out in that Explorer, if I multiply velocity and time together, I get distance. So how long is the slide? That's distance. That's rate times time. And I have rate and time. That means do the definite integral. So this is not telling me to count squares. You have to interpret that to mean, oh, that's where I've got to count the squares and multiply by the area of a square. So go ahead, hit pause again, count up your squares, see what you come up with. You can turn it back on, got 21.3 squares. Or did I? Oh, I don't think I made my graph different. Oh, I guess I better take the time to do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. I always count the whole ones first. I made my scales different on the one I did in my notes, so I got to recount. Plus, now my partials, I'll go 0.6, 0.1, 0.9, 0.3. Oh, I'll count that one as a, could have counted that as a whole. 0.5, not going to count that. 0.7, 0.1, 0.9, 0.2, 0.8, 0.2, 0.9, 0.1, 0.7. Okay, counting those up. 6, 7, 10, 1 plus 1.8 plus, oops, not even on the right screen. 1 plus 1.8 plus 1 plus 1 plus 1.2 plus 0.7, 7.9. So I got plus 33, 40.9 squares. Now I've got to multiply by the area of a square. And the size of my squares, I went by 1/2 and by 1. So the area of one square, 0.5, is 0.5. So 40.9 times by 1/2, I'm going to get 20.45. And the units here would be feet. So I got about a 20-foot slide. And the author said it's 21.3. So I'm in the ballpark. Hopefully you were too. All right, we're not done yet. It said at approximately what rate was her velocity changing at time 3? So part E, at what rate was velocity, which is our y value, changing at time 3? Okay, that rate, that's our derivative, that's our 3-point table. So I want to do a 3-point table around 3. So I'm going to go close to 3. I'm going to stick with that 1/100th away. So my 2.99, 3, and 3.01. Okay, I'm going to use my table features, the table set. I want to have it start at 2.99 and go by 0.01. Now when I go to the table, all those values are going to be there. So 7.81458, 7.83327. Oh, did I miss this? I think that should have been a 9 on the rounding. And then the 3.01, 7.851882. Kind of ran into my stuff. I should have had a bigger piece of paper. Okay, but you know what to do from here. We're going to do the change in y over change in x and average those two together. Okay, I'm just going to do them on the calculator because I don't have much room to write them. So I'm going to take this one, subtract this one. So 7.83327 minus 7.81459, divide by 0.01. I get 1.868 on the top. On the bottom, 7.851882 minus 7.83327, divide by 0.01, 1.8612. If I average those together, $1.865. And let's see what units we should have there. We're dividing feet per second divided by seconds. So let's see what happens there. Feet per second divided by seconds. Well, think about it. I can't leave a fraction within the fraction here. Make this a fraction by putting it over 1. If you go back to junior high, when you divide fractions, you flip the bottom one and multiply it by the top. So I have feet per second multiplied by this reciprocal. So feet per second times by 1 over seconds. Multiply tops, I get feet. Second times second is second squared. Feet per second squared. And if you know physics, you'll well, maybe you don't know now or yet, but distance per time squared is acceleration. So what we just found, and that's the answer to F, is acceleration. We found her acceleration at time 3. Okay, I believe that is the end of this section. Your assignment then is going to be, and again, this is in class tomorrow, page 16. Quickies 1 through 6. Quickie 1 through Quickie 6. I'll show you the quickies real quick. I haven't assigned them yet. The rate at the beginning says do these quickly. I call them quickies. You should be able to do all 10 in less than 5 minutes. I'm only giving you 1 through 6. These are just real quick. They may not be anything we've done recently. It's all just usually just past knowledge stuff. And then after that, I'm going to give you the problems that relate back to the notes that we just took. So quickies 1 through quickie 6, and then you're going to pick up number 2, 4 through 9, 12 and 13. Okay.